Hi, I'm Jaiyoung Park, graduate student from Seoul National University, advised by Professor Jung-ho An. Today, I introduce me and my colleagues' work to run neural networks on encrypted data. Our implementation can run a ResNet20 model on an NVIDIA A100 GPU in just 1.4 seconds, enabling secure and fast analysis of sensitive data. We've also prepared an exciting demo to showcase our implementation in action, so stay tuned. We first start by introducing homomorphic encryption and the problem of private inference. Homomorphic encryption, HE, is an encryption scheme that enables direct computation on encrypted data. Using HE, one can securely outsource computation to cloud servers, enabling private AI inference. In this scenario, client transmits encrypted images to cloud server, and server computes neural network with HE operations. Finally, once client receives encrypted result, she can decrypt and see the result. Among many HE schemes, we set out to use the ResNet20, which supports fixed-point data type. However, the performance gap is huge. FHE operations, for example multiplication, are approximately 10,000 times slower than the unencrypted counterpart. In addition, as shown in figures, complex workloads such as private inference slows down further. To solve this problem, we propose a multifaceted approach to accelerate FHE-based neural network. Our contributions are threefold: optimized GPU implementation, low degree activation function, and convolution algorithm having lower rotation count. Before we deep into our work, we provide a short introduction of our ResNet20, which supports arithmetic operations such as addition, multiplication, and cycling rotation. In ResNet20, encryption process transforms a message, which is a complex vector of size half of n, into a ciphertext. A ciphertext consists of L+1 ring polynomials of degree n. Here, L represents level, which is a HE-specific resource. Multiplication uniquely consumes level, so as the program proceeds, you may need to use all available levels. If you run out of levels, you can use bootstrapping to restore them, and enable more HE operations. More sophisticated HE schemes that support bootstrapping are classified as fully homomorphic encryption. Now we change our gear and present our contributions briefly. A single FHE operation consists of multiple primitive HE functions, including number theoretic transform and base conversion. Though these primitive functions are highly parallelizable, they are bottlenecked by memory bandwidth on GPU. Furthermore, existing optimizations such as RNS decomposition are biased toward reducing the computation. Such bias often leads to severe memory bandwidth bottleneck on GPU. To address this issue, we debunk optimal HE settings for GPU and utilize memory-centric optimizations such as kernel fusion and reordering of primitive functions. Next, I introduce our new activation normalization method called ASPA. Previous works have used high-degree polynomials as activation functions, but they suffer from high computational overhead. ASPA replaces batch normalization and ReLU with the composition of Helmholtz expansion and basis-wise normalization. Our experiments show that ASPA achieves comparable accuracy to ReLU and can be simplified to a scalar function during inference. Next, I introduce our convolution methodology called hyphen. We identified that HE rotation is the primary bottleneck in previous FHE convolutions. The majority of these rotations are used to aggregate channels within the same ciphertext and maintain a single data organization. In contrast, hyphen replaces rotations with cheaper additions to aggregate channels and use various data organizations and alternate between them to remove rotation overhead to maintain a single data organization. To briefly summarize our result, our GPU implementation shows 7 times and 257 times speedup over the prior GPU and CPU implementation, and our polynomial activation function is 75 times cheaper than the prior polynomial activation. And lastly, our convolution algorithm are 3 times faster than the prior convolution algorithm. In conclusion, considering ResNet20, we brings down the latency from 2271 seconds to 1.4 seconds. Finally, welcome to our demo showcasing the power of encrypted ResNet20 Inference. Let's start by importing some necessary libraries that enable us to perform secure computation. Now, let's define the network and load the pre-trained weight to the GPU. This step includes encoding the weight, which may take some time. Next, we will show you the power of encryption. First, we get a test image and print it, and it is cat. Then, let's encrypt the image and print it. As you can see, the image is secure. Finally, let's run the inference. The first iteration takes 1.6 seconds as it is warm up, and the result is decrypted to cat. But after that, we will run it for 10 iterations, and you will witness the speed and accuracy of our encrypted ResNet inference. Thank you.